So now let's look at cycle-based tests. So in cycle-based tests, they're very simple in the sense of we use a cycle ergometer, that might be a weight-loaded cycle ergometer like a Monarch, or we use an electronically controlled cycle ergometer like the Loader. And in essence, the principle is fairly simple, that you ask the participant to cycle as hard as they can, and we record power. Now this is where cycle tests really stand out from the jump and the running based tests, because they have an ability to estimate power in real time. Now there are a number of different tests, and the first one I'm going to show you was put forward back in the 70s and the 80s as a measure of power, and it's a constant load cycle test. So all that simply means is that the participant has a fixed resistance applied, so nothing changes, fixed resistance is applied, and they work as hard as they possibly can against that resistance. So in this example, it's a test to volitional exhaustion against a fixed resistance of 400 watts for males, 350 watts for males, and they're looking for cadences of between 124 to 128 for males and 104 to 108 for females. It's really as hard as you can possibly go. And what's measured, or what's estimated, is the total amount of work that's done. You also take a blood lactate at the end of the test. But the key thing to understand here is, this is why I want to breeze over this, is that's not a measure of power. It's not a measure of power, is it? All you're doing is measuring basically how long somebody can go for. It's a time trial. It's not a measure of power. In essence, one would argue it is not, as you'll see when we look at the anaerobic capacity in a subsequent session. One would argue, well, it's closer to a measure of anaerobic capacity because it's how long somebody can sustain this for. It's not measuring power, because it's not about the rate at which the work is done. It's about how long somebody can go for. So it's a performance time trial. It's absolutely not what the authors were telling you. So I thought I would show you that, because I think it's fundamental to kind of remind us about what we mean by power. That notwithstanding, they reckoned it got fairly good reliability, but they looked at it with a correlation. Actually, if you try this on a test-retest basis, what you'll see is in the second trial, participants go for a lot shorter time than in the first trial. Don't worry about why at the moment, but if I tell you that that is due to the notion of pacing and what is called teleanticipation, you may want to go right and have a little read around that. So let's go back to this schematic that we've seen in previous sessions, which is the schematic from Heck and colleagues. And it tells us that fundamentally, that if we're doing any form of test and we're trying to estimate the power, then we know that we're kind of looking at peak turnover rates in anything from really, 1.5 seconds. But by the time we get to 10 seconds, we've pretty much depleted the high energy phosphate pool. You can see that with the PCR trace sitting in the middle of this schematic. So anything longer than that, like that constant load test, has got nothing to do with power. So we're looking for short duration tests, as we had with the jumping tests. So if we look at this data here, what you can see is just an estimation of how intense one of these tests would be. In this example here, what you can see is the watts per kilogram that somebody's working at, and the MAP is the line which refers to their maximal aerobic power. That's VO2 max. So what you can see is, in this example here, their VO2 max was at probably something like 4 watts per kilogram. What they're actually working at when you're trying to estimate anaerobic power is much, much higher. We're looking at 15, 20 watts per kilogram. But notice what you see in that plot there, it's over 30 seconds, looks very similar to what you're seeing here. Look at the decline in PCR. You get the same thing in terms of the decline in power. You get the high ATP turnover rates. It's exactly what you'd expect, isn't it? High ATP turnover rates for 3 to 6 seconds, then the PCR is less available. We rely on glycolysis. If you remember, the glycolytic ATP turnover rate is half as rapid as it was from PCR, but it can be sustained for longer, so power declines. You get a very rapid drop, power declines. We can maintain that for a period of time, and then it perhaps drops a little bit more. So what you're seeing here is kind of an estimation of what's going on anaerobically potentially over a 30-second trial. But does it need to be 30 seconds? If you're referring to the power, then the power is really what's occurring in this first time phase, in this example, within the first 5 seconds of the test. So the most common way of doing this in terms of using cycloergometry is to use the Wingate test, developed originally by Ailon, but really the godfather of this is Bar-Or, and then his colleague Inbar. And basically the original idea is to use a Monarch or equivalent weight-loaded cycloergometer, as you can see in this image here, and as you'll see in a subsequent video. And the way it works, quite simply, it's a fixed resistance for 30 seconds. And that fixed resistance is anything between, depends on kind of the study that you're working with, or the group you're working with, it's anywhere between about 7 to 8.5% of body mass. Very much depends upon the group. Now that, of course, in itself throws in variability. If that's not consistent, and you go and get tested in one institution at 7%, another institution does 7.5% of your body mass, you change the resistance, which changes your ability to accelerate the pedals. So 7.5 kilograms, maybe you can do this for arms as well. So this is quite nice. It allows us to have upper body power, because you can use upper body arm ergometry for this. The beauty of this is that the authors refer to the notion of determining peak power, mean power, power decline, and fatigue index. Now, what you have to ask yourself quite simply is, if we're assessing anaerobic power, do we really need to know mean power, power decline, and fatigue index? And then you've got to ask yourself a really important parameter in the kind of the overall notion of the test: how anaerobic is a Wingate test? And we'll come back to that in a moment. But this is conventionally what happens. In the test, the participant accelerates the pedals, the resistance is dropped onto the flywheel, and it's suddenly like putting the brakes on your bike, but you have to keep pedaling as hard as you can. So of course what that does is it applies a resistance onto the muscle, a load onto the muscle, so the ATP turnover rate accelerates. And therefore, the amount of power we're producing also must increase. So what happens, you can see here, we've got these repeat blocks, these every 3 seconds, I think, 3, 6, 9, 12, yeah, every 3 seconds. So what you can see here is that the highest power output was achieved within the first 3 seconds, and in this case, this schematic is at 750 watts. You can then work out the fatigue index, which is the highest power minus the lowest power, divided by the highest power times 100. And that's meant to be kind of an index of somebody's anaerobic sustainability. Well, let's focus on two things. Firstly, if we're trying to estimate peak power, why does the test need to be 30 seconds? So that's a really important message. That's about efficacy in testing. If all you're interested in is peak power, why go for 30 seconds? Because you're putting somebody through, in this case, 27 seconds of purgatory, because it's horrible, because you're just going and going and going and going and going, and you're not going to use any of the data. If you are interested in the fatigue index and so on, then that's a different question. So does it need to be 30 seconds? Well, the original Wingate test was designed because you could record not only peak power, but mean power. They refer to anaerobic capacity, which again, we'll debunk that in the next session, which is anaerobic capacity. But I then posed that question, which is, well, how anaerobic is this test? And let me just explain why I'm posing that question. And to do that, let's just go back a couple of slides just to help us. So if we go back to this slide here, here we've got a 12 to 14 second response. 14 seconds is the solid line, 12 seconds is the dashed line. But look, yes, there is a decline in PCR. Yes, there's a rise in glycolysis. So there's clearly an anaerobic glycolytic response. Remember that DLA DT, which is delta lactate delta time, is our proxy indicator of anaerobic glycolysis. But the important one to look at is that pink line that shows VO2. There is an aerobic contribution. We understood that. We've seen that in previous sessions where we referred to the fact that all the energy systems are operating simultaneously. They absolutely are. So there is an aerobic contribution to the test. So in a Wingate test, how do you know that when you're referring to, for example, let's just go forward, when you're referring to, for example, fatigue index, or you're referring to anaerobic capacity, how do you know it's anaerobic? You don't know because there's an aerobic contribution to that test. And in fact, Ralph Benneker published a really nice study back in 2003 in the European Journal of Applied Physiology, which estimated that 27% of the entire test was anaerobic. And in fact, if we go back and refer to the work that we, in the previous session, which was from Greg Gaetanos, and in that previous session, you may want to go back and look at it, but we referred to some pie charts, and we showed the estimation of an aerobic contribution within 3 seconds. And even in a 3-second contribution, it was estimated that maybe up to a 10% aerobic contribution. So even using this test, remember, you're estimating power. You can't be certain that all the energy that's being used has been derived from non-oxidative sources. So really have to have a word of caution on that in terms of thinking about this. Yes, it looks more robust because I'm getting a resistance and they drop the resistance on and I have to accelerate against it, therefore the amount of ATP I need must accelerate. Yes. But don't just assume that acceleration in the ATP turnover rate has come from the high energy phosphates. There is also a glycolytic contribution. There is also an aerobic contribution. And I just wanted to show you this. This is quite interesting. So in this example here, what we've got is we've got a number of different approaches. I'm just going to turn my head to make sure that I'm actually reading this correctly for you. And that what they've got is endurance trained athletes doing the Wingate test. And what they've done is they've measured the blood lactate response across the 30-second test. So we're kind of just moving away from power at the moment. So park power and just think, okay, this is just about the whole test. Look at the glycolytic contribution to this test. Massive glycolytic contribution. So it has quite significant ramifications, but also notice what's happening in the first 5 seconds. In the first 5 seconds, there is still a relatively high glycolytic contribution. So even at that start of that test, it's not just about the high energy phosphates, it's actually about, to a certain degree, substrate level glycolysis. That's fine because it's the highest power output, but it is worth bearing that in mind. Now, I want to show you this data which is from Doughton and colleagues, published in EJAP back in 2006. Because what they write is this: the Wingate anaerobic test was primarily intended as a test of glycolytic power. That's what Bar-Or stated, glycolytic power. Think about it. How do you get to the glycolytic power? Represented by what was termed the mean power. So in other words, they were taking the mean power output across the whole test, irrespective of how much of that was ATP PC, how much of that was aerobic, how much of that was glycolytic, and going, well, that mean power is glycolytic power. The Wingate's 30-second duration was chosen for being sufficiently long, not only for eliciting maximal glycolytic power, but for requiring a good measure of glycolytic anaerobic endurance as well. It sounds very confused in terms of what the test was meant to be doing. But they go on to write this: peak power was a byproduct, it was a secondary thought, a secondary parameter defined as the highest 5-second power output, which was not necessarily the first 5 seconds. And this is an issue. If you've got a software that is sampling and is just sampling on 5-second rates or 3-second rates, how precise is that? So one of the things to think about is that you need to be using up-to-date cycloergometers that allow you to record power in real time, so that they're sampling at a fast rate. So the newer Monarchs enable us to kind of record on 1 second averaging. If you use something like a Loader, which is an electronically controlled cycloergometer, it has a sampling rate, I think of 1,000 hertz. So that means 1,000 samples per second. So you can be much, much more precise in how long it takes to reach peak power, and therefore what the peak power is.